A warm welcome to part 2 of the lecture on limits. In the previous lecture, we gave some motivation as to why limits are important in analysis. We then defined sequences and discussed the concept of the limit of a sequence. This was done because it is easier to understand the concept of a limit in the context of sequence rather than in the context of a function. We then defined neighborhoods and finally formulated a rigorous definition of limit in the language of neighborhood of a number. In this lecture, we will briefly recapitulate again the definition of a limit and we'll see some other examples of converging sequences. Let Xn be a real or complex sequence and let L be a number which is real or complex depending upon the case. We say that limit Xn as n tends to infinity is equal to L if for any given epsilon greater than 0 there exists a natural number n such that mod of Xn minus L is less than epsilon for all n greater than equal to n. In the language of neighborhoods, this is restated in the following way. Given any neighborhood of L, that is n epsilon L, there exists a natural number capital N such that for all n greater than equal to capital N, all terms of the sequence Xn lie in this neighborhood. That is, Xn belongs to n epsilon L for all n greater than equal to capital N. The notion of convergence of a sequence conveys the intuitive idea that the terms of the sequence lie arbitrarily close to the limit point for all n which are large enough. Towards the end in the previous lecture, we saw an example of a sequence which converged to 0. That sequence was xn equal to minus 1 to the power n by n. Let us see a few more examples of converging sequences. The first one is that of a constant sequence xn equal to a for all n belonging to the set of natural numbers. We claim that Xn converges to A itself. It is very easy to see why is that. Mod of Xn minus A is equal to A minus A, which is 0, and 0 is less than any epsilon which is positive. And this is true for all n greater than equal to 1. Thus, according to our definition, Xn converges to A. As a second example, consider the sequence xn equal to z to the power n by n, where mod z is equal to 1. Now, our guess is that this sequence should also converge to 0. And why is that? That is because if you look at the numerator, it is z to the power n. The modulus of the numerator is fixed, which is 1, whereas the denominator being equal to n becomes arbitrarily large. Therefore, we expect the modulus of this ratio to be as small as we like by taking n large enough. And this is what we are going to show formally, that xn converges to 0. So, mod xn minus 0 is equal to mod of z to the power n by n, which is equal to just 1 by n because mod z is equal to 1. Now, by taking n large enough, 1 by n can be made smaller than any epsilon. Precisely this can be done by choosing a natural number capital N which is greater than 1 by epsilon and considering all values of small n which are larger than this chosen value of capital N. Thus Xn converges to 0 as n goes to infinity. Another example is Xn equal to z to the power n, where mod z is less than 1. Here also we may guess that the sequence converges to 0 because if you take the modulus of the sequence, you get a real number with magnitude less than 1 raised to the power n. Now, any real number with magnitude less than 1, if you raise it to the power n and take n larger and larger, that number is going to become smaller and smaller. For example, 1 by 2 raised to the power n will become smaller and smaller and will approach 0 as n becomes larger and larger. Therefore, our guess is that this sequence should also converge to 0, and we will prove it rigorously. Since mod z is less than 1, this implies that 1 by mod z is greater than 1. Let us take 1 by mod z equal to 1 plus p, where p is some positive number. Then 1 by mod z to the power n is equal to 1 plus p to the power n, and this is greater than np, and this follows directly from the binomial expansion of this term. So if you expand this term, the first two terms will be 1 plus np and the remaining terms. So overall, this sum will be greater than np. So we have shown that 1 by mod z to the power n is greater than np, or mod of z to the power n is less than 1 by np. Now by taking n large enough, as we have been doing all this while, we can make this term smaller than epsilon. More precisely, for all n greater than equal to capital N, where capital N is chosen such that 1 by capital N times p is less than epsilon, we can assure that modulus of z to the power n is less than epsilon. Thus, z to the power n goes to 0 as n goes to infinity. In the remaining part of this lecture, our concern will be to give some propositions and facts which will help us conclude whether a certain sequence converges or not, without having to use the basic definition of the convergence of a sequence. So in that direction, let me first propose proposition 1, which is, let xn be a sequence and let L be a number. Let k be some fixed but arbitrarily chosen integer. Then the proposition says that xn goes to L if and only if the sequence xn plus a goes to L, as n tends to infinity. Basically, this proposition says that the limiting behavior of a sequence remains unaltered if you ignore finitely many terms from the beginning, because the sequence xn plus k is same as the sequence xn, but we are looking at it after k plus 1th term. So the proposition says that both the sequences xn and xn plus k either converge together or diverge together. It cannot happen that one of the sequence converges and the other doesn't. Let us see a quick proof of this. First, let us suppose that xn goes to L. This implies, by definition, that for any given epsilon greater than 0, there exists a natural number n such that mod of xn minus L is less than epsilon for all n greater than equal to capital N. But then this implies that mod of xn plus k minus L is also less than epsilon for all n greater than equal to n minus k, or if you wish, you can just take n itself. Hence, by definition, xn plus k tends to L as n goes to infinity. Now, suppose that xn plus k goes to L as n goes to infinity. This implies that modulus of xn plus k minus L is less than epsilon for all n greater than equal to some natural number n. This implies mod of xn minus L is less than epsilon for all n greater than equal to capital N plus k. And hence, by definition, we can conclude that xn goes to L as n tends to infinity. Conclusion of this proposition is, as I have already mentioned, the limiting behavior of the sequence remains unaltered if a finite number of terms in the sequence are ignored. As a corollary of this proposition, let us consider the sequence which is xn equal to a for all n greater than equal to n naught. We have already seen that the sequence xn equal to a for all n converges to a. By virtue of the previous proposition, if we ignore finitely many terms from the beginning and consider a sequence which becomes constant after finitely many terms, that is, yn is equal to a for all n greater than equal to n naught, then this sequence yn also converges to a because the constant sequence, as we have shown, converges to a. Consider another proposition, proposition 2, which states that the limit of a converging sequence is unique. In other words, a sequence has at most one limit. We will prove this by assuming that a converging sequence converges to two numbers L and L prime, and then we will finally show that L is same as L prime. So let epsilon greater than 0 be given. Then by virtue of the fact that both L and L prime are limits of the sequence xn, there exist natural numbers n1 and n2 such that mod of xn minus L is less than epsilon by 2 for all n greater than equal to n1, and mod of xn minus L prime is also less than epsilon by 2 for all n greater than equal to n2. By the triangle inequality, we can write that mod of L minus L prime is less than equal to mod of L minus xn plus mod of xn minus L prime. And this is valid for all n. Now, in particular, if we choose n which is larger than both n1 and n2, then this inequality simply reduces to mod of L minus L prime is less than epsilon. But epsilon is an arbitrarily chosen small positive number. So this inequality implies that L is equal to L prime, which is exactly what we wanted to show. Let us see another proposition, proposition 3, which says that a convergent sequence xn is bounded. In other words, there exists a positive real number m such that mod of xn is less than equal to m for all n belonging to the set of natural numbers. Let us see a quick proof. Since xn tends to L as n tends to infinity, by virtue of the definition of the limit, there exists a natural number n naught such that mod of xn minus L is less than 1 for all n greater than equal to n naught. Here we have just chosen epsilon to be equal to 1. Now we define m in the following way. M is defined as the max of mod of x1 minus L, mod of x2 minus L, mod of xn naught minus 1 minus L plus 1. Let small n belong to the set of natural numbers. If small n is less than n naught, then mod of xn minus L is less than equal to max of mod of x1 minus L up to mod of xn naught minus 1 minus L. And this is certainly less than m by virtue of the definition of m. If n naught is greater than equal to if n is greater than equal to n naught, then mod of xn minus L is less than 1 because n naught was chosen in such a way that for all n greater than equal to n naught, mod of xn minus L is less than 1, and 1 is less than m as we have defined it. So we conclude that for all natural numbers, mod xn minus L is less than m. Now by using the reverse triangle inequality, we can conclude that mod of xn is less than mod of L plus m. Thus we can catch hold of a positive real number which is mod L plus m, which is strictly greater than mod xn for all n. Thus we conclude that xn is a bounded sequence. The utility of this proposition is that if we have to check the convergence of a sequence and if we find that the sequence is unbounded, we can immediately conclude that the sequence does not converge, because if it were to converge, then the terms of the sequence must form a bounded set. We will illustrate this to an example later in this lecture. Now, before proceeding further, it is important to make a few definitions because the propositions which are going to follow rest heavily upon these definitions. So the first definition is the following. A sequence xn of real numbers is said to be bounded above if there exists a real number m such that xn is less than equal to m for all n belonging to the set of natural numbers. This number m is said to be an upper bound of the set formed by the terms of the sequence. Similarly, a sequence xn of real numbers is said to be bounded below if there exists a real number m such that all terms of the sequence xn are greater than or equal to m. In that case, m is said to be a lower bound of the set formed by the terms of the sequence. The least upper bound or supremum. Let A be a non-empty subset of R which is bounded above. That is, A is less than or equal to m for all A belonging to the set A, where m is some real number. The least upper bound or supremum of the set A is a number m tilde belonging to R such that the following two properties are true. First one is m tilde must be an upper bound of A, and as the name suggests least upper bound, any number smaller than m tilde should not be an upper bound of the set A. In other words, if you take epsilon greater than 0, then there must exist an element A of the set capital A such that m tilde minus epsilon is strictly less than A. In other words, there is an element in the set A which is strictly bigger than m tilde minus epsilon, which is smaller than m tilde. So any number smaller than m tilde will not be an upper bound of the set A. Similarly, let A be a non-empty subset of R which is bounded below. That is, there exists a real number m such that m is less than or equal to A for all A belonging to the set A. Then m is a lower bound of A. The greatest lower bound or infimum of A is a number m tilde satisfying the following two properties. First, m tilde must be a lower bound of the set A. That is, m tilde must be less than or equal to A for all A belonging to the set A. And any number greater than m tilde must not be a lower bound of A. In other words, if you take an epsilon greater than 0, then there must exist an element small a in the set capital A such that small a is strictly less than m tilde plus epsilon. So any number larger than m tilde will fail to be a lower bound of the set A because there will exist an element small a which is strictly smaller than this number m tilde plus epsilon. Let us see some examples. Consider the sequence xn equal to 1 minus 1 by n. Clearly, xn is less than 1 for all n. So 1 is an upper bound of the set 1 minus 1 by n, where n belongs to the set of natural numbers. In fact, any number greater than 1 is also an upper bound of this set, as you can easily check. We claim that 1 is not just an upper bound of this set, but it is also the least upper bound or supremum of this set. In order to check this, we just have to make sure that any number smaller than 1 is not an upper bound of this set. So let epsilon be greater than 0 and choose a natural number n which is greater than 1 by epsilon. So this implies that 1 by n is less than epsilon, and hence 1 minus 1 by n is greater than 1 minus epsilon. So we conclude that there is an element, namely 1 minus 1 by n, belonging to this set which is strictly bigger than the number 1 minus epsilon. Hence, any number smaller than 1 will not serve as an upper bound of this set. And hence, 1 is the least upper bound or supremum of this set, formed by the terms of the sequence xn. Consider another sequence xn equal to 1 by n for all n belonging to the set of natural numbers. Clearly, 0 is less than 1 by n for all n, and hence by definition 0 is a lower bound of the set formed by the terms of this sequence. We claim that 0 is actually the infimum of this set. For that, we need to check that any number greater than 0 is not a lower bound. So let epsilon be greater than 0 and choose capital N greater than 1 by epsilon. This implies that 1 by capital N is less than epsilon. Thus, there exists a term 1 by capital N, which belongs to this set, which is smaller than epsilon, where epsilon is any positive number. Thus we conclude that 0 is actually the infimum of the set formed by the terms of the sequence, because any number greater than 0, which is say epsilon, fails to be a lower bound for the terms of this sequence. Thus infimum of the set 1 by n such that n belongs to the set of natural numbers is equal to 0. I'll stop at this point. In the next lecture, I will suggest 2 more propositions which will help us immensely in concluding the convergence of a sequence to a particular limit without having to resort to the first principles. Thank you.